hope you guys enjoy it. My name is Tim Poth. I am a Senior Priority Response Analyst for Bentley Systems. We've got a couple of slides here that I'm just going to slam through really quick. I'm going to talk about Bentley. I'm going to talk about my team. I'm going to talk about what applications we primarily support with Wireshark. And then we're going to get right into the packet captures. And that'll be the good stuff. So I'm just really going to go fast in these first couple of slides.
Are these slides going to be up on the website?
Yes, I submitted all this to Janice. I was looking this morning. I haven't the slightest idea where this is going to be posted. I have also submitted all my capture files. I haven't the slightest idea where they're going to be posted.
She's busy.
Yeah. My email address is on the first slide. We can go back to that at the end. If anybody wants to email me or get a copy of this stuff before it's posted or anything along those lines, feel free to drop me a line. I'll be back in the office Monday and I'll start trying to reply to things. So, this is right off the Bentley website. Bentley is a global leader dedicated to providing architects, engineers, contractors, owner-operators with comprehensive software and solutions for sustaining infrastructure.
I assume you mean architects and so on for building physical buildings?
Correct.
Okay.
We have two core products. We have MicroStation, which is a CAD platform. If you've ever seen AutoCAD, it's the same thing, it's just better. We also have a document management system called ProjectWise. The claim to fame on this system is that it understands and tracks references in engineering documents. If you're not an engineer, it's really not terribly important. I'm with the PRT team. We primarily support two applications with Wireshark. It is ProjectWise, our document management system, and Select Server. Select Server is our licensing system. It records product usages so that we can hopefully get paid by the people who are generating value in the product. So, what do we use Wireshark for? When a company, when an end user has a problem with one of our applications, we're often dealing with the end user, we're often dealing with the application level administrator, not the network administrator, to try to figure out what's going on. We use Wireshark to understand how our application is behaving on their network and to track down any obstacles it's running into. Sometimes it's broken devices, sometimes it's misconfigured devices or misconfigured DNS settings. Sometimes it's flat bugs in our product. We don't like to admit it, but it does happen, and we do actually learn a lot using Wireshark on our application. The real value for us is using Wireshark to prove what's broken. It's really easy for me to go to the networking team and say, I think it's something on your network that's broken. That's not going to get anywhere really quick, and that starts a lot of patch line. With Wireshark, I can go and say, look, here are the packets. This is where things are not going well. You need to look at this device. And it's a much better conversation at that point. So, real glossy overview on ProjectWise, just so you guys know what terms I'm talking about as I go through my presentation. ProjectWise is a client-server application. We use a proprietary protocol on port 5800. It has nothing to do with VNC. A lot of people hear 5800 and think, oh, VNC, no, that's absolutely nothing to do with that. We use 5800 first. They just were slightly more popular than us. This product's very old.
It better be.
Yeah, we got there first. They were just more popular. We use something called Delta File Transfer in newer versions to speed up file transfers. Basically, if you've got a 1 meg file but you only change one line of it, we send the one line across, not the whole file. There's plenty of math that goes into doing that. The details are fairly important. Each file transfer starts off with a new TCP connection. This is interesting to note because as we go through the capture files, anytime you see a SYN, SYNAC, ACK, we know that that's a three-way handshake for a TCP connection. There's a good chance that we're doing something new. We're doing a file transfer, we're doing a new application start, we're doing something that's going to connect back to the server. It is kind of silly to do it that way. We actually have started reusing connections for file transfer in later versions, but for all the stuff we're going to be looking at, it's a nice indicator. It kind of keys on what we're looking for. The application supports application-specific gateway and routing terms. So you've got your network routing and your network gateway, but we can also route traffic between ProjectWise servers. Lets us do fun and interesting things. We have an integration server, gateway server, caching server, and web server. The integration server is going to be your database server. It's going to be the core server that connects into the database. The gateway server is the gateway that helps route stuff between different places. Caching server is where files are going to be stored. The web server is the web server. The web component is an ASPX page. It uses ActiveX for file transfer. A data source is a collection of files and folders and metadata hosted on a server. One server can have many data sources. Each data source can have many storage locations. Select Server is our licensing product. This is an IIS.NET application that records and processes usage in a database. It's really straightforward. We use SOAP over HTTPS. I don't know how many people are familiar with SOAP. It's a simple object access protocol. It's not simple, it's a silly name. It's basically XML data in an HTTP request. Rather than downloading an XML file, you're just streaming an XML file. It's really not that fancy. We have a reporting component that publishes usage data via an ASPX page. We're actually going to look at an example of that. And Bentley hosts a public instance on the internet that clients can use. Large organizations also like to deploy their own local instance of the software. The local instance ultimately communicates back to the public instance so we can collect all of our usage data. If you see a 127 IP address in the capture file, that is a valid IP address. I was hex editing these things in bulk and I picked a random hex value and I didn't bother to check what it goes to. I don't hex edit often. So when I started opening up my captures after I got done all of my changes, I noticed I made a terrible choice. But I was lazy and I didn't go back and fix it all. So just consider 127 a valid address. If you look at any of my TCP checksums, IP checksums, a lot of them are trashed. Don't pay any attention to any of the checksums, any of the packets. They have nothing to do with what's going on in the trace, and a lot of it's because I was hex editing. So a lot of it just got booted up. This is a participation required session. I want you guys to speak up. I want you guys to talk. I'm going to try to interactively take us through the captures. I don't want to just stand up here and explain to you what I found. I want us to go through it as a group. So we'll see how that goes. So to the fun part. Hopefully that wasn't too painful. Issue number 1. ProjectWise long client launch. The user is complaining about how long it takes ProjectWise to open and display data sources. The capture is from a gateway server. The reason we got it from the gateway server is because of this little log snip we have down here. Hope you guys can see my mouse. If you look here, we have a start request, and then we have a send to socket. So you can see the server's acknowledging that it's going to do something, and then we're actually going to start sending the data. If you look at the timestamps here, though, we go from 2545 to 2552. There's 7 seconds in there. That seems like a long time. That seems like it's a possible reason why the users wouldn't be happy. So this is from the gateway server, so we figured, well, let's get a capture from the gateway server.
I assume all the machines are type C?
Reasonably, yeah. This log is from the gateway server, so we can see the request came in and we can see it's 7 seconds before the gateway server decided to do something. So there's something taking a lot of time on the gateway server. So we pop over to the capture. And we've got a lot of different things going on in this capture. You can see that it's almost 400 packets long. So we could go ahead and we could look through the whole thing. But I don't know, that's 400 packets is a lot to look for. So because I come from the application side, I like to filter down on the application right off the bat. So we use port 5800, so what do you guys think we can do to try to narrow things down a little bit here? Yeah, filter down on the port list. You guys still hear me? No? That any better? I'll just try to speak up here. So, as the gentleman up front said, I'm sorry I didn't catch your name. We can go ahead and just filter down on the application. TCP.port equals 5800. So this brings us right down to our application. This shows us exactly where we are, what we're doing here. Now, I have some columns that are a little different than the default Wireshark. I changed my time column over to show hours, minutes, seconds. The reason I do this is because I reference Wireshark back to application logs quite a little bit. As you saw in the logs before, we had timestamps in our logs, so I can cross-reference that to timestamps in Wireshark. I also added a delta column in here. Now, if you look right here, what do we see in the delta column? You see a 6.5 second delay. Well, that's interesting because in our logs we're seeing just about a 7 second delay. So, hey, there might be a correlation here. You know, we might have an idea what's going on. If you look at the packet number here, we go from 87
to 174. Well, we got a big delay, there's stuff going on, but why do we have a delay? Maybe it has something to do with some of those packets going on in between. Might not, shot in the dark, but it's worth a guess. So, if we look here, we've got some different IP addresses. I happen to know, it probably should have been included in the slide, the IP address we're interested here is this 2.6 address.
Could you maybe try and blow up the numbers a little bit? I'm not close and I'm having trouble seeing it. Other people have had more trouble.
Is that better for you guys?
It's better for me. I don't know about people further back.
All the way in the back, you guys like that? Alright, excellent. See if I can resize these columns here a little bit. Hopefully that's not too confusing. So I happen to know here that the box of interest here is this 2.6 box. It's the 29 is our client actually coming in, which makes the 2.6 our server that we're actually on. So if we go ahead and we filter down on just that box's IP address, we can see right here, this is the last ProjectWise packet right before the gap, and this is where we come back. Well, what do we happen to see in between? There's name resolution, there's DNS name resolution, and there's also NBNS. NBNS is NetBIOS name server. I don't know if you guys are familiar with how NetBIOS works. With DNS, when you ask a question, when you get a response back, it's going to say, oh, there was no answer, it's a definitive answer, I'm going to move on. NetBIOS, it's a broadcast type mechanism, so if we don't get an answer, we don't know if we didn't get an answer because there was no answer, if we didn't get an answer because somebody just didn't hear us. So this is really Bueller. Eventually I'm going to give up, but you know, I've got to ask a couple of times. Maybe Bueller fell asleep and I got to wake him back up. So if you look here, we're going through and we're resolving a couple of different names, and we get down to this one name and we get a no such response. And we try again with a different DNS suffix and same deal. So DNS goes ahead and gives up on it, but it turns it over to NBNS, and it sits here and it asks and it asks and it asks. There was a response packet in here. That response packet is actually for something a little bit different. So what do we think might be going on here?
DNS problem.
This server probably should be in DNS. Turns out that this user has configured this in their application configuration. They never bothered to tell DNS about it. And so every time they go ahead and launch the client from this particular office, they're trying to resolve this particular server, it just sits there and spins and spins and spins. That's why the users are unhappy. Everybody feel good about this? Any questions? Making sense? Okay. So I have an answer slide here. If you go back and look at it later, it's pretty much everything we just talked about. So here we have a slow file download. The user is seeing delays downloading files through the ProjectWise gateway server. The log files didn't show anything useful. We went ahead and we captured from the gateway server. Why did we capture from the gateway server? We took a look at the logs and we made a guess that that would be a good place to capture. So this is a little bit larger of a capture. We've got about 3,000 packets in this capture. So where's a decent place to start? Well, we can go ahead and filter down on the application. In this particular instance, it didn't really filter out that much. Some of these captures are pretty concise down to us, but the user's seeing a delay. So what can we kind of key in off of that? Ah, come on, you guys are all far too quiet. The user seeing a delay might be a delta. It might be that simple. We can just go ahead and look for a delta and see what's going on. So if we go ahead and sort by our delta column, We see an 11-second delta here before a SYN. It's the beginning of a conversation. That may or may not be that terribly interesting. We have a couple other packets in here that have got 16, 16, 15-second delays in here. That seems pretty significant. That seems like if a user was complaining about 7 seconds in the previous capture, user complaining about 16 seconds, I mean, that really could be a point of agitation. So if we go ahead and leave that guy selected, if we go ahead and resort by number, what do we see? This is the packet that has the delay. What do we see right before that?
Acknowledgement.
Well, we see an acknowledgement, but if you go up a couple of frames, we actually see a SYN, SYNAC, and an ACK. We know that to be the beginning of a TCP handshake. If we take a look at these port numbers here, we can see that this, come on in. Plenty of seats, don't be bashful. We can see that there are, or as we talked about earlier, we always start off a new file transfer. We always start stuff off with a new TCP stream. So if they're downloading the file, and we've got a new TCP stream starting off here, and we immediately have a 16-second delay, might be related. There might be some correlation in here. If we look, we've got a couple of packets in between this delay. Might be related to the issue, might not be related to the issue, but if we go ahead and clear our filter, we can actually take a look at what's in there. So there's actually two problems we're seeing on the screen here. What do you guys think? What do we see on the screen here?
You have a destination unreachable for ICMP, and you have a server failure on DNS.
You're right. Now what's the correlation between these?
Can't get there.
But who can't get there? If you look at these IP addresses, who is making the DNS request? The DNS request is coming from 10.20. The DNS server, we've got a couple of DNS servers we're bothering here. I believe there's 3 or 4 of them. Who do we get the response back from? We get the response back from one of our DNS servers, but who sends out the ICMP packet?
Client.
The client. Why in the heck would a client tell a server that it can't be reached? If we look at this ICMP, get my windows scrunched up a little bit here, you can see that this ICMP packet is in response to the request that came in right above. So why, the server was generous enough to give us an answer. Why did we tell the server that it can't get to where it's going? The key is if you look at the delta column again. Delta column is one of my favorite columns to look at. For an application side of things, it helps reveal a lot. If you look at that DNS response, server failure, it took 7 seconds for that response to come back. One of the neat things about the Wireshark dissector is if you come in here, you can actually see what packet that request came in on. So we can see that the response is in response to a request in 1234. So we sent the request here, we got the response back 7 seconds later. If we look at the next instance of this, where we've got a response and then a ICMP unreachable, this packet actually is in response to 1233. So if you come, we're all the way up here to get a response back here.
It looks like 12, 33, 34, 35 are being sent at the same time. Okay, no, they're being sent to different destinations.
Right, we're communicating to multiple different servers. The client is really trying here. Come on, somebody, there's got to be a DNS server out there that can get me an answer.
I'm going to bet you the cache is wrong.
Well, there's 2 problems here. 3 problems here. So why is our client sending these ICMP packets back? Well, destination unreachable, port unreachable means that the client wasn't listening for a response on that port. Why wasn't the client listening to a response on that port? It timed out. If I send out a request on the network, I'm only going to wait so long before that response comes back. It's going to vary from client to client, but in this case it's taking the server 7 seconds to bother to get back to us with a response. We've closed down the DNS requester at that point. We're not waiting for the server to come back anymore. We've just thrown up our hands and moved on. So that's why our clients are sending out these ICMP packets. But the bigger issue is, why in the name of all that's good on the network is it taking a DNS server 7 seconds to get back or 8 seconds to get back with a response after we sent all these requests? I mean, these are a lot of DNS requests to not get a response back. Turned out that the user actually had this server configured to point to the wrong DNS servers. And because they were the wrong DNS servers, it was taking a real convoluted path to get there. It wasn't something the server should have been doing in the first place, so there was nothing set up on the network to enable it to go quickly. The next problem is that we don't bother to get a response back. The user actually didn't have the reverse lookup zone set up correctly, so we just never were going to get a valid response back for this. And the third problem here, and it's kind of obfuscated, but we don't get a valid response back to this, and yet the transfer continues to work anyway. So did our document management system really need to look up the address in the first place? No, we shouldn't have been doing it. Good intentions, but it just was a waste of time. So we have this 16-second delay here for our user getting the file, all because of a silly reverse lookup address. So you guys good on this capture? Any questions? Awful quiet back there in the back. So this is one of my favorite trace files here. User is having problems downloading files from ProjectWise. We're getting error messages in our logs, we're getting error message on the screen. They make absolutely no sense whatsoever in any universe. They're weird, they're twisted, something's terribly wrong here. I had absolutely no idea what was wrong, and I had absolutely no idea what to do. So they're downloading a file that's kind of network related. I'll go fishing with Wireshark. When in doubt, I get a Wireshark. Doesn't always work out, but in this particular case, it came up really interesting. So, the first thing I normally do is filter down on the application traffic, but in this case, I already said that the error messages we're getting back at an application level don't make any sense. So, does it make sense to filter down on the application layer?
Maybe.
We filter on the application layer. I always like to see how many packets we're going to capture. It gives me a fuzzy idea of what's going on. Well, what do we see here with this capture? There are 13,000 packets in this capture. Almost 5,000 of them are ProjectWise packets. Well, I don't know, that's really disproportionate. That's kind of interesting. If I go to the top, we can see that this was captured at 6 minutes, 6 seconds. If I go to the bottom here, we can see that the capture was stopped at 16 minutes, 22 seconds. So we've got roughly 10 minutes worth of time here. So in 10 minutes worth of time, this client did 13,000 packets, and close to a third of them were the application we're actually dealing with here. Might be nothing, might not be important, but that seems a little funny to me. I mean, that seems a little off. So what is all this other traffic that's going on? So I like to just start scrolling through. What do we notice as we start to scroll through?
UDP.
There's a lot of UDP traffic. Some of it's just UDP and some of it's DNS. Well, I'm going to kind of key in on the DNS first. I actually know what DNS is. I don't know what these weird UDP packets are. So what's funny about these DNS packets? We're doing a reverse lookup for a 68 address. We're doing it for a 207 address, 68 address. We've got a response coming back from a Comcast. I don't know if you guys know Comcast is an ISP. It's a cable provider. If we look down here a little bit more, we've got some more different IP addresses, 74 address, 91 address. We've got, Bell Canada. We've got Charter, we've got Rogers, we've got Op Online, Kogo Cable, Bell South. Is that weird to anybody else?
Sounds like a spam agent.
It's something.
Botnet, spammer.
we look here, I mean, this client is really popular. I hope I have my syntax correct. This guy's really popular. I mean, we're just talking to people all over the world. I don't know if we'll see it as I scroll through here, but we're talking to people in Portugal at one point. I mean, we've got a Japan address right there on the screen. I mean, we're talking to everybody. This guy's really popular. This is a server, mail server. You know, I might understand that a little bit. But this is Joe Below client out in the office. I mean, this is just, I don't know, it's weird. So what does Joe do? He's an engineer. He's a drafter. He's supposed to be designing a building or a road or something along those lines. He's just a poor lowly engineer. He's not supposed to be this popular in the whole world. So if we take a look at some of these UDP packets here, this is the other thing that caught me as being a little bit strange. What do the ports on these UDP packets tell us? Well, they don't tell us anything definitive. I mean, what port does web traffic go over? Whatever port you want. It's kind of a loose indicator.
Well, web traffic isn't UDP.
Well, no, but it's an example. What does a port tell us? It doesn't really tell us anything definitive. Anything can go over anything. But if we look at the port numbers here, I mean, these are really high port numbers. I mean, all of them in this page are well above 10,000. Normally, once you get above 10,000, those are normally random port ranges. Well, to have a random source and a random destination port range, and that's a little funny. It doesn't tell us anything definitive, but that's a little funny. If you guys watch this part of the screen here, particularly the text part, yeah. If you see in here, if we scroll through the different packets, what word is reoccurring in there? Line. Doesn't have to be a signature, but normally if you see something, especially plain text like that, reoccurring over and over again, that's normally a signature. In this particular case, as the gentleman over here said, it turns out this is a signature for LimeWire. A little playing around on Google or whatever your favorite search engine is. This is a LimeWire signature here. So, just for fun, what do people like to download on LimeWire? Songs. What was that?
Porn.
Well, this guy's at work, so he's not going to do that. He's got at least a little bit of...
He's not a politician?
He's not a politician. So we're going to go ahead and run a search here. We're doing a string, we're doing text here. We're going to look here in the packet bytes. This is going to look down here in the often the garbage section that you can't really tell much from. So hey, we've got a hit here. What do we got? We got Beyonce. Do we go ahead and search again? We got Britney Spears.
No Justin Bieber.
No Justin Bieber. This is from a couple of years ago. The Bieb hadn't become that big yet. So we caught somebody doing something a little they shouldn't be doing here. This guy kind of has LimeWire loaded up on his box. So how does this relate back to our document management system not working correctly? Beats the heck out of me, but they probably shouldn't have LimeWire on their work computer. So we said to the IT department, you know, probably should take that off. Maybe it's traffic related, I don't know. Take it off, give it another try, see what happens. Well, it fixed the issue. So we found the cause, but I still don't understand what the cause was. A little bit more investigating, what we found out is the user was on Windows XP. Windows XP did some things to limit the number of ports that you use, especially on the UDP end of things, and it directly impacted the ability for these peer-to-peer applications to work. So what did the peer-to-peer applications do? They wrote their own version of a DLL that Windows was using so that they could do things the way they wanted. Well, we were just blindly calling into Windows some network functions. We said, Windows, go send a packet, go get me the returns from a packet. Well, we were calling into their DLL without realizing it. They just loaded their DLL into memory and we were just calling the functions. Their DLL was not working the same way as the Windows DLL, and it resulted in weird behavior, which resulted in our applications just not working correctly.
I think it's more than that. I think the person had a LimeWire server, and the connections from all the world where people trying to pull music files from his system.
Well, LimeWire is a true peer-to-peer system, so it's not just a client-server. Everybody's a client and everybody's a server.
Understood.
So once you come out...
There are too many connections being made in the time period for the guy to just be downloading music for himself.
You're correct. But it wasn't the number of connections that was impacting this user's box. If it was that simple, he would have taken the entire office down. His Outlook wouldn't have worked. I mean,
Right.
nothing would have worked. It was specific to our application didn't work. And it happened to be the specific network calls that we were making. If you load LineWire up on a box, even if you're not connecting to anybody, even if you're not doing anything, the presence of that DLL will just trash your application.
Right. Also, good antivirus should detect LineWire, say that it shouldn't be there.
Well, that's a debate for the antivirus vendors.
Or might just scan.
I'll leave that to a different argument, but
It wasn't just a bandwidth issue.
no, this had nothing to do with bandwidth. It had nothing to do with what they were doing with LineWire. It was just that silly DLL dropping on the box. Got the guy in a fair amount of trouble, so come on in, plenty of seats. So we've got another example here. Another user trying to download a file. Our users, it's a document management system, they like to get files out, so it's a frequent point of problem. So the user's trying to download a file and it causes ProjectWise client, PWC, to hang. The logs make it look like we're waiting on the server. So what do? Well, we went and we captured traffic from the client and from the server. I want you guys to see the answers yet. I shouldn't have clicked on that slide. Go ahead and try to open up both of these. We'll go ahead and we'll start over on the client side. So if the user's downloading a file and it's hanging, where do we start?
At the beginning.
Well,
Take a look at the handshake, see if it's got started okay.
Well, we can see here we've got a fair amount of traffic going on. Normally when a user calls up and tells me, well, I started to download and it hung, they usually stop the capture about the time that it hangs. It's usually actually at the bottom. If you go to the bottom, you can normally see what the last thing the client did. If that's where it stopped, there's a good chance. It's a reasonable place to start. So we're going to move these down just a little bit. We can see right here on the screen, we've got a SYN, SYNAC, ACK, beginning of a handshake. So we know that file transfers start off their own session, so we've got a reasonable guess that this might be the file transfer here. And we've got some packets, and the capture just stops. Nothing terribly exciting about this. This has already been filtered down to the application, so you don't get to see all the other stuff going on in the network, but it just stops. That's interesting. It kind of supports what the client said, that it just kind of hangs there. Not terribly exciting on the client side. We switch over to the server side. This again has already been filtered down on the conversation. Where do we go? Go back down to the bottom again. Ooh, that doesn't look good. What do we have going on here? Unreachable, but it's a little funny. We've got traffic flowing up here. Why does it stop all of a sudden?
Yep.
If we look at the top half of this, and I'm not going to sit here and count packets, but we've got roughly 15 packets here. If we swing over here, yeah, we got close to 15 packets here. So we can see that the client and server had started a communication. They're starting to go back and forth with things. If you look at these packet lengths, I don't have a length column here, I probably should. You can see these were all reasonably small packets. You know, 5, 176, 56, 56, 168. What might these be? Probably not a file transfer. I mean, it's kind of silly to bounce all over the place with a file transfer with these kind of packet sizes. These actually are a little bit of application communication. Hey, I want this file, these are my credentials, this is what we're doing today. So it's the client and the server talking a little bit about what they want to do. So it seems like that's working okay. You know, we've got the request coming in from the client here. The client is 241, so we've got the server sending out some data, we've got a response, server sending something out, we've got a response. Looking at some of these lengths, you know, this may have actually been a request from the client, we get a response back from the server. So this part of the conversation's going well. When we get down here, what do we see happen to the length of our packets? Well, they're all the same, but they're also very big. 1380, 1380, 1380. These are not necessarily full-size packets, but these are fairly large packets. Depending on the network, this might be the limit of their MTU. This is probably a data stream. This is probably our file actually being transferred. We've got it going on. So we get a whole bunch of these through. We never get a response back from the client. That's when the ICMP packets start. So what does this indicate to us? The ICMP packets start right when the file stream starts. So maybe the file has something in it, has done something to agitate whatever this device is. I happen to know that this one.dot device is their firewall. But we went back to the user and we said, well, what is this device? What is it doing? They go, oh, well, it's a firewall. Is it just a plain firewall? Is it like a little Soho firewall? Or, oh no, it's a big fancy, I'll say Cisco, I don't remember what it was. It's a big fancy firewall. We've got security stuff on there. We've got intrusion prevention. We've got digital leak prevention. We've got all kinds of stuff on there.
It only acknowledged up to 993 for the last several packets. Didn't get any farther.
Right, well that's because we never got anything back from the client, but if you notice the sequence number keeps growing here.
Yeah.
So we're sending data, but we're never getting anything back from the client. What it turned out was we took this cache and we went back to the user and we go, well this 118.1 device, this is telling us that we can't get to the person that we were just talking to packets beforehand. And it's once the file transfer starts. Can we go take a look at this device and take a look at the warnings and the errors and the logs on this thing? It turned out that the way the user had the security settings on this, as soon as we tried to fire up a file transfer, the firewall got very upset with what we were doing and it just shut down the communication. And then
That port?
this session, it's actually the address port pairing combination. This user has multiple offices that all interconnect, but they have firewalls in between each office. And this firewall just did not want to allow a client from another office to come in and communicate. So it was very simple. It was just a misconfiguration on their firewall. Luckily, their firewall was polite enough to respond back with these ICMP packets and tell us that we can't do what we want to do, rather than just eating the traffic and disappearing it.
I'm just curious, why do they have firewalls between each office? Are they different divisions?
It's a security architecture. They had VPN links in between each offices. They put a firewall on the inside of a VPN. They figured, well, if one office had something terrible happen, arguably it wouldn't be able to propagate to the other offices. Is it right? Is it wrong? It's just what these guys chose to do. It was a...
It's common to have the firewall operate finance.
So they're different departments.
In this particular case, it was at an office level rather than a department level. There's a lot of IT groups that firewall off the server rooms from the rest of the general network, just as a filtering mechanism. Just different architectures. This was a Department of Transportation, I believe. So they took a little bit more of a paranoid approach to things. And right, wrong, or indifferent, they just had their settings tweaked their own direction, and it caused us all kinds of headache. So, we've looked at 4 project-wise examples. I get tired of project-wise after a while, so I'm going to cut over here to select server. This is a bit of a complicated one. This actually took a lot of time to track down. The user is trying to run a summary report off of the select server hosted by Bentley, and they're getting errors back from the proxy server. They were very upfront with us. They said, hey, our proxy server is very unhappy about the responses getting back from your server. I believe it was a connection reset error message back. Well, that's odd. The user went ahead and they captured this from their proxy server, and they stopped the capture as soon as the error message came up. I make a note of that because, again, we can use that as a key. Well, if they stopped it as soon as it happened, then maybe the problem's towards the end. I also have a working example here that is the same procedure, but it completed without a problem. This was done from my laptop back in the office. So we'll go ahead and we'll start on the not working side. And we'll just go ahead and scroll down to the bottom here. And we can see that the last request we did here is a ASPX page that we're hitting, and we're pulling a summary report. But that seems like it might be where the problem is. Our user's complaint was they couldn't get a summary report, so sounds like a good place to start looking. What do we see here after the summary report completes? The user finishes sending their stuff, so this is a post request, so we're sending data up to the server. The server at Bentley, the 64 address is a Bentley server. We go ahead and we acknowledge it, and then we reset the connection. And we do that in pretty short order. It takes about 175 milliseconds for us to get that reset back. What might it be? Where might our problem lie? Nothing really at a network level that jumps off and grabs us. I don't see retransmits. I don't see ICMP packets where we're not filtering down to anything, so it's not like I have weird DNS going on here. I don't see anything at a network level that's wrong. I mean, this seems pretty straightforward. Well, if it's at a network level, what might it be? Might be at a data level. Maybe something about the request we send isn't quite right. So what can we do to actually easily see all the data that's in this particular stream? We can click on the packets here and we can look at the reassembly, but I don't know, that's an ugly window. I can't stand trying to look at stuff like that. We right click on the packet. There's a phenomenal feature in Wireshark here called Follow TCP Stream. And when looking at data-specific issues, this is one of my favorite things to do. This here, we've stripped out all the TCP level stuff. We've stripped out all the ACKs and resets and all that stuff. What we have here is just the data. This is the data that was the request. And we can see it comes up very nice and clean. Red is going to be the data that our client sent to the server. Blue would be the server's response back. Well, we don't see any server response back because we didn't get anything back at an application level. The server TCP acknowledged it and then TCP reset us. So at an application level, there's not a lot going on. So we've got this data here. Is this right? Is this wrong? Is this good? Is this bad? Beats the heck out of me. I am the slice. Well, it's not necessarily encrypted. If you look here, it's a cookie. So it's kind of hashed. It's kind of a mess. But I haven't the slightest idea whether this is good, bad, or indifferent. I don't know what it's supposed to look like. So when you get into a situation where you just don't know what the traffic's supposed to look like, what's the best thing to do? Go capture a working copy. I mean, if you can take a working copy and a non-working copy, there's got to be something different between them, right? I mean, yeah, the timestamps are going to be different. My username and their username are going to be different, but there's got to be something meaningful that I can line up side by side and say, aha, that's where it must be. So we've got my working capture. What's the easiest way to find exactly what I'm looking for on the working capture? I'll go ahead and capture or copy off the post request here. If I'm doing the exact same thing that the user is, then I've got to be able to find the exact same post request. So if we come over here to my working copy, we'll just very simply go ahead and do a find. We'll go ahead and do a string. Now the last time I did a find, I did it in packet bytes. So that's because we were looking down in the actual payload of the packet for a particular string. We were looking for this silly user and his MP3s. In this particular case, because HTTP is going to go ahead and be dissected up here in the info column, I can actually leave it looking through the packet list. And this will make it run a little bit quicker, especially on large captures. I don't have to go through all the bytes of every single solitary packet. I can just skim through the info list and it finds a lot quicker. And we'll go ahead and we do a search and it pops right up. Now there's a reset that comes in right after that. You might be inclined to say, oh, well there's a reset ACK right after your request. Well, if you actually look at the ports that we're on, if I can keep resizing these windows, it makes life difficult. For the request, the source port was 1102. The reset in this case came in on 1104. So you might see that right afterwards, but it's actually for completely different conversations. You always got to be careful what you're looking at, what stream you're on. So if I want to go ahead and compare this side by side, what's the easiest way to do it? Go ahead and follow the screen again. Go ahead and make it pop right out. Now if you see, this is a lot longer and this has a lot more data in that. Why is it? It's because this was the actual working case. So we requested it and we also got some replies back. So we'll go ahead and find in here. We'll go ahead and find for that string again. And that takes us down right to where the post request is. Now it's highlighted up here in black. It's just the way the find box highlights. As I scroll down, we're going to lose the top half of that. Don't worry about the top half. It's just the way it scrolls. You can't get them to line up perfectly. So we've got a broken example here, and we've got a working example here. What's important to look at in here?
If they're broken.
Well, the difference, but there's lots of things that could be different. If we look up here at the top, we can see my user agent. It's MSIE 6, Windows NT 5.1. We flip over the .NET CLRs are a little bit different. I've got DSG support. What's DSG support? I don't know. It's something to put on the list of things to look into and why it might be different. So as we flip back and forth here, we can see that there's a lot of different things that are different. And unfortunately, there's no good, easy way to say, well, you need to look at this first, you need to look at that first. You kind of need to look at everything and try to roll it in and try to roll it out. So I looked at a lot of the header information, and I couldn't find anything one way or the other that really was definitive on where the problem might be. So if you've been to any hands-on sessions, and if you haven't, I strongly recommend you go to at least one at some point. He always tells you to look for patterns. That's something I really like to do, is look for patterns. So I'm going to go ahead and I'm going to flip back and forth here a couple of different times. And don't focus in on one part of the screen. Don't try to read every line. Just kind of let your eyes go a touch fuzzy, and anything other than the blue highlighting at the top, jump out and grab anybody as being really different between these two files.
One of them seems to have some sort of a proxy header.
If you look here, the formatting right in here is different. We've got a lot of dead space off to the right. That's actually what caught my eye first. If you look in this one, it's much more compressed. We have a session pending URL and an event target. If we look here, we've got the session pending, the event target, but there seems to be this stuff shoved in the middle.
You got blue code blockage?
This is in the cookie section. And is it legitimate for people to shove stuff in the middle of a cookie? No, not really. In this particular case, the user had a blue code firewall, or a blue code proxy server. And we knew, he told us up front he had a proxy server, so we called this guy back and we go to him, so what kind of proxy server are you guys using? Oh, we're using blue code. Aha! Why is your blue code proxy server injecting keep alive data into the middle of our cookie? Blue Code's a very good company. I don't want anybody to think I'm coming down hard on Blue Code. We all make mistakes. Blue Code made a little mistake, and the way we presented our cookie and the way that they parsed through it, they thought that this was an okay place to shove some keep alive data, and it wasn't. Blue Code released a patch for this. So the problem is that this data's been injected into the packet. Well, how does that relate back to what we actually saw? The client sent the data up. We have here, the client sent the data, the server acknowledged the data, and then the server reset the data. How does that being in the cookie actually relate back to what we're seeing here in the client?
When you're modifying the cookie, right? So wouldn't it have a bad reaction? Like saying that it's not valid?
Exactly. We went back and we talked to the network team that managed the firewall in front of these servers, and we say, hey, we're gonna run a couple of tests. Can you let us know if anything funny happens? They came back to us and they said, yeah, it was really weird. We kept seeing these bad cookie error messages come through in the intrusion prevention system, and it was just kicking out the cookies. Why are we getting all these bad cookies? Blue Code injecting it in there probably would have upset the application, but it wasn't even getting to the application layer, which is why we didn't get an application error message back. The intrusion prevention system took a look at the cookie and it said, that's not cool. I don't know what this garbage is in the middle of the cookie, but that's not a valid cookie format. So it went ahead and it just kicked it out right there, and that's why it reset the connection with the user, which is why their proxy server told the user, hey, your connection got reset. Yeah, just stop putting stuff in my cookies. So Blue Coat was actually really nice to work with on this, and they cranked out a patch for our user really quickly, and it worked out really well. So we've got another really kind of tricky one here. Users trying to download a license from Bentley, and they're getting a message that the license is invalid. We took the capture here from the client. Now this has already been filtered down to HTTP. So where do we start? What do we want to look at here?
What's the problem they're reporting?
The license is invalid. We're trying to request the license, and it's coming down invalid. Well, if it's coming down invalid, what's the license look like? I'm curious. So if we go ahead and follow stream here, it's the easiest way to pull this out. We can see that we're doing a post request here. We're going to the gateway. We're doing a get license. So that's good. We know we're looking at the right stuff. And then we've got the license here. Well, what's the license? It's SOAP data. What's SOAP data? It's XML. So what do we know about XML? It always has to start and it always has to finish with the brackets. It's got the little less than, tag, greater than sign, opens and closes. It actually kind of looks like HTML code. So if we go ahead and we skim down through here, what do we see when we get to the very end of this? Yeah, that's not complete. Something kind of cut this off right in the middle. So, all right, well, the user's not crazy. They are getting an invalid license. So we know it's not an application bug per se. So why is my license getting cut off? Where's a good place to start? The bottom. It gets cut off at the end. I like to go to the end. So this is weird. What do we see going on here? Well, we've got a reset, but we've got two resets here. And if you look at the flow here, I'm going to go ahead and back up just a little bit here. So we've got data, data, acknowledgement, data, data, acknowledgement, reset from who? Looks like reset from the server.
There's no fin.
Then we get, it doesn't always have to be a fin. But we acknowledge the server, and then the server resets us. But what's the very next packet here? What do I have highlighted in blue? It's more data from the server.
Is it unreasonable to have that many reassembled? Almost all of those seem to be reassembled.
It's a big stream. If we go back to the
I think that's also a Wireshark coding, right?
well, the reassembly just means that it's data that's part of a stream. So if you're transferring 100 megs worth of data, you're going to have whatever the packet count for that is of reassembled stream. If we look here in the original request, we can actually see where the server tells us the content length. The content length in this case is going to be a little over 100K. So we're going to have a lot of packets that are going to constitute this. So the reassembly is okay. It just means that these are data packets. You know, data, data, act, data, data, act, data, data, act. But what do we act the server resets us, and then what's the server do? It sends us more data. Well, that doesn't seem to make a lot of sense to me. I mean, why am I going to tell you, I'm done talking to you, by the way, I have something else for you? No, that's not valid. That's kind of against the rules of TCP. So what do we see as the very last packet in here? Well, the client resets the server. Why does the client reset the server? The client resets the server because it knows that what the server just did doesn't make any sense. You shut down the conversation. We are not talking. Why did you give me more data? We're not talking. Maybe you forgot you told me we're not talking anymore, so I'm going to remind you that we're not talking anymore. So the client reset's understandable, but this whole reset and more data, that doesn't make a lot of sense. Now I'm going to point you guys back over to the delta column. What can the delta column seem to indicate for us in this particular case? We look here at the data packets coming in, what do we see? We've got roughly an average of a 7 millisecond latency. I can scroll up and down, but it's roughly the average of 7 milliseconds. So this is a pretty good connection. I mean, 7 milliseconds, that's great. So it seems like every data packet that comes in from the server is about 7 milliseconds. What happens with this reset packet that comes in from the server? That didn't come in 7 milliseconds, that came in less than half a millisecond. That's pretty snappy. Somebody gave that internet connection a whole lot of coffee there or something. I mean, that's just... Or maybe it didn't come from the internet. Something speeds up that quickly.
Proxy server.
Maybe it came local. I don't know at this point if they have proxy or what they have, but they've got to have something. These are private IP addresses in here. So
I saw a Barracuda sign in there, so it's got to be that.
be careful how much you key in on. You're right, there is a Barracuda signature in here, but it actually had nothing to do with Barracuda. But it is definitely a very good observation. If we look at the sequence numbers here, the sequence and the ACK number, they line up. So that's kind of interesting in its own right. So it's not like this is something that, oh, it really got sent 7 seconds ago and it just came in out of order, or it came in late, or... No, this is actually a reset to the ACK packet we just sent, and this came back in less than half a millisecond. So, So why maybe did this packet come in from the local? And if it did come in local, why was it sent as a reset spoofing our server? Why wasn't it set as, you know, like an ICMP response from a firewall, or you know, why was it something a little bit more friendly? So this is a bit of a cooker. What do we look at here? Well, I like to look for patterns. So if this reset is in response to that ACK packet, maybe there's something wrong with the ACK packet. I don't know what could be wrong, but you know, maybe there's something wrong. If there's something wrong with the ACK packet, what can we use to compare it to? Well, previous ACK packets. So at this level, when I'm trying to find something that's wrong, if I'm going to say that one ACK packet has got to be buggered up in some way, what am I looking at in all the ACK packets? I'm looking at everything because I haven't the slightest idea what could possibly be wrong. I'm going to be looking at options, and I'm going to be looking at port numbers, and I'm going to be looking at everything in there. So this took quite a bit of time before it actually caught my eye, but if you guys go ahead and focus in on this middle frame here, and I'm not going to expand anything. You just go ahead and focus in on the middle frame. As I'm clicking through these packets here, don't really see a lot changing. When I get down to the bad packet, anybody notice anything that changed? I'll go ahead and just flip between these two guys here real quick.
Yeah, the map of the...
It's not the internet protocol.
Destination, the MAC address changed.
Very good. It was the MAC address. If we look at the good packet, if we look at all the prior good packets, we're hitting this Cisco CA. I'm just going to go down to the last 2 bytes in there. We're hitting this Cisco CA device. When we get down to the bad packet, we're hitting a Cisco 7D device. Aha! Why did the client just hop devices on us?
Is that a feature in Wireshark that would pick that up more easily? Because I noticed all illegal activity here, but it'd be cool to see that kind of...
If we come in here to conversations, it does kind of show up that we're talking to 3 different devices. This is actually your Barracuda device here. What this user had, if we took a little bit more time to look at the packets, is actually had a weird asynchronous system set up where the packet would come in through the firewall, it would go to the Barracuda, the Barracuda would send it on to the user would send the acknowledgement back around to the router, completely bypassing Barracuda for reasons well beyond my understanding, and then that would go back out to the server. It worked for them. I don't know their exact setup. I didn't get to look at their config, so it's hard for me to explain why it worked. But it worked up until this point, so I'm just gonna take that off the table. It does kind of pop out here that we've switched routers. We've got 3 packets going to this, but if you don't realize which 3 packets those are, if you don't realize where they fall, it can be difficult to say, well, we'll come in here and look to see if you're hopping routers. I mean, who would ever think that a client's just going to hop to a different router in the middle of a conversation? It's not a sensible thing to do. So
people would think that it's a problem coming from the sources you're downloading from the development.
Me and this user actually had quite a bit of an argument because he said, no, it is not my firewalls, it is your server because it's your server's IP address. yeah, but no. So we went to the user and we said, what the heck are you guys doing with these Cisco devices here? And they go, oh, well, those are my firewalls. I have load balanced firewalls. We go, oh, that's interesting. We've got 2 firewalls. For reasons I don't understand, the user never bothered to tell us how they fixed it. This client was randomly flopping between their 2 firewalls. I almost want to say it was dead gateway detection, but obviously the gateway wasn't dead when we decided to flip over. So when the client flipped over to the other firewall and tried to send this acknowledgement packet, the firewall very understandingly said, well, you don't have a conversation set up through me. I haven't the slightest idea of why you're sending me this packet. I'm just going to reset you because you must be an error. Yeah, it's a security device. Okay, it takes that perspective. I can kind of see that.
I used to have that. I used to work for Nobel. So when I had all the support calls, they have a customer had a middle tier server, but all the connection that flipped over were like disconnected and had to reconnect on the second one. So all their previous streams are all cut off.
Yeah. So in this particular case, our stream's getting cut off in the middle. Now, why did the user only notice this when they were trying to pull down a license? Our license file, if you look at the reassembly, if you look at the reassembly here, we get to about 36K of data before this happens. Well, how big are most web pages? They're not 36K. How big are most images on a web page? They're getting closer to 36K, but you're still not really at 36K. If you go to wireshark.org and 1 image or 2 images on that site doesn't load correctly, are you going to notice? Maybe if it's the Wireshark banner across the top, but you're not really going to notice, and if an image just doesn't load right, you're going to go, oh, stupid Wireshark.com, the image didn't load right. Whatever, they must be having problems today. So this was something that was affecting all the users' communication, but it wasn't until they got to a larger download, 100K download, where they actually saw the problem crop up.
And every time they had a file or a transfer that long, the servers would change, or the route would change through?
Yeah, it wasn't a very specific size, but it was when a connection was open for a certain amount of time, the longer the file, the more probable you have the problem. The client says, oh, I'm going to go to this firewall. Oh, I'm going to go to this firewall. I'm going to go to this one. I don't know why. I have the slightest idea. It was...
You'd think it'd be causing a lot more trouble than just your license.
The user was working off of internal mail servers and internal file servers, and they were doing a lot of internal stuff, so it was just internet-based stuff.
Well, we know they weren't using LimeWire.
They weren't using LimeWire, so that was a positive in this particular case. So we're going to stay on the select server theme here for just a little bit longer. User is trying to push some data to Bentley select server and is failing with an error message. Captures from the client. So we're still back here in the HTTP request because this is still select server. And what do we see? I mean, we've only got 100 packets here, but what can we do to kind of get a little bit better idea of what's going on? Well, if we go ahead and filter on HTTP, I'm not telling you to always filter on HTTP, but if we do filter on HTTP, it takes all the ACKs and all the SYNs and all the TCP level stuff out, and it lets us see just the HTTP communication. And this can be useful to help narrow down and try to get a cleaner view of what's going on. Well, what do we see? We see a 417 failed. It's probably not good. How can we look into that a little bit further? Follow the stream. So we go ahead and maximize this here. We see we're doing a request, we're doing a post to this this particular page. I don't know what that page does, but it's important to us. And we get our response back here. What's this look like here? It's HTML. Well, that's kind of nice.
Look towards the bottom. Yeah, follow the arrows and kind of acknowledge request.
It's Stewie's fault.
It's Stewie's fault, exactly. We can go ahead and we can read through this. I'm lazy. I don't really feel like trying to interpret HTML. That's what web browsers are for. So what we can do is we can go ahead and copy that. And I can go ahead and create a blank web page on my desktop. I can actually go ahead and paste the content right in there. And when I go ahead and open this up with web browser, eventually, there we go. It actually goes and it renders it for us, and it makes it really nice. You know, this is a terribly complex page. We could have read through it ourselves, but it's kind of nice just to let this come up. It's also really nice to go back to the user. You don't want to give the user HTML code. That's just going to create problems. But if you go back to the user and say, this is the page that came up, this is a lot more friendly. So we can see that it's an error at the top, but what can we see about the request itself? There's a couple of different things we can key in on here. We can see that we're doing a post and it's an HTML 1.1 request. We can see our UTF-8. We can see our content length. We can see that we have a 100 continue here. We can see that it's tagged as an invalid request. Okay, that's interesting. Why is it invalid? It goes ahead and it gives us some idea on why it thinks it's invalid. Missing or unknown method, missing URL, missing HTTP identifier, HTTP 1.0. Well, that's weird, because up here at the top it identified it as an HTTP 1.1. So why is it missing a 1.0 identifier if it already told me it was a 1.1 HTTP request? If we look down here at the very bottom, you might have noticed this in the when we follow the stream here, it's also up at the top. You can see that the server here is Squid. And that shows up down here again as Squid. Squid is an open source proxy product. It's a phenomenal proxy. It's actually baked into a tremendous amount of products and you don't even realize that you're running Squid. So we know what application we're having trouble with and we know roughly what the error message is. So how do we bring this one home for our users? How do we get them back up and running?
Is the connection keep alive? This is not a cookie, is it?
No. If we actually look at the request, wrong frame, we're just sending a request and we've just got a little bit of SOAP data in there. It's really not much to this request at all. What we did is we went ahead and we took that it's Squid and it's HTTP 1.1 and we're getting a 1.0 error message and we went up to the web and we started looking around and we actually found that there is a HTTP standard when it comes to dealing with proxy servers that Squid interpreted one way and everybody else interpreted slightly different. If you actually look at the standard, it kind of looks like Squid did follow the standard absolutely correct and everybody else was kind of off, but everybody else was kind of off. Well, I don't care how right you are, if everybody else is doing something a little bit different, you kind of have to go their route. So this was actually a known issue with Squid, and very begrudgingly, well before this issue came up, Squid actually posted a fix for their product, and this user was just running an old version. And the type of request we sent was getting into this gray area with Squid where they weren't, us and them were on two different pages on what the request should actually look like and how it should be formatted. So, kind of got us into a sticky point with Squid, but. So how long's this session run? We're about 20 minutes here, so.
So Squid fixed it? Or
Yeah,
they
Squid.
just updated or the client updated the Squid.
Yeah, they went ahead and they applied a patch and it took care of it. So it was nice, it was easy. This user didn't fight us too much. We got one more example here on Select Server before I get bored with Select Server and go back to ProductWise. The user is trying to use the license management tool to get a license from the Select Server. It is failing. License management tool is a tool to manage licenses. It lives over on the client side. So went ahead and got a capture from the client. So we've got a request here. What can we do to kind of filter this down a little bit? We can go ahead and filter on HTTP again. I mean, again, it's not the only way to look at HTTP traffic, but it does tend to condense it down and take out some of the errors so we can try to get a better feel for what the commands are doing. Now I'm going to draw your attention to the very first packet here. Does anybody know what WPAD is? WPAD is Web Proxy Auto Discovery. What you can do is you can create an entry in your DNS server, and when most modern browsers come up, they will go ahead and they will make a DNS query, and they will say, do you have a WPAD entry? If there is a WPAD, it will bring down a server name. DNS query for the name, it comes back with the server. It will go ahead and it will make a request to that server for WPAD.dat.
Is that the option in Explorer that says auto detect proxy server?
Exactly. WPAD.dat is more or less a JavaScript file. It's not exactly JavaScript, but it kind of looks like JavaScript. That is a proxy auto configuration. So depending on what websites you're hitting and depending on what address you're coming from, you can see that this client's shoving the users out different proxies. Is this what the problem is? Absolutely not. But this is a really nice identifier. It gives you an idea, hey, the user is using a proxy, they do have proxy auto discovery on, and we know what rules the client is using to determine what proxy to go out. So it gives us a lot of insight to the user's network without having to ask them any questions and spend a lot of time. So we know that they're using a proxy server. What can we see from these communications here? There's one thing on this page that jumps out and grabs a lot of people, and they start to go down the wrong path with it. And was that?
Big delta.
No, it's asking for the proxies requirement authentication.
You got what a lot of people get. A lot of people look over in the side and they go, oh, there's proxy authentication required. You're not authenticating to the proxy. It's a very easy thing for a lot of people to jump to, but if you actually take some time and look through it, it's actually not the case. The way most proxy authentications work is it's challenge response. So what happens here is the client made a request for nodelock.asmx, and the proxy server challenges it, and they said, well, you need authentication to get to this page. I can't just let you there. So what's the very next request? Well, the very next request, see if I can make that line a little bigger. You can kind of see it. The very next request, we're looking for the exact same page, and we have some user information in there. The user information looks really weird because I went in with a hex editor to try to obfuscate it, and I kind of broke the way it did it, but you guys don't need the username anyway, so it's good. So what do we see back? Well, we see another authentication back, but we see now an NTLM-SSP challenge response. Again, the malformed is because I was in there playing. So this is part of the challenge response. So we go ahead and we make the request one more time, we send a little bit more user data across, and this time we're going to get a response back. So it's not an authentication problem. It's really easy to jump to that conclusion off the bat, but it's not an authentication problem. We're actually authenticating quite nicely. Now you actually jump to exactly where the problem is. Again, I love my delta column. I reference my delta column quite a little bit. What do we see right here? We see a 30-second delta from that post request. Well, what happens at the end of the 30 seconds? We make the same post request over again. 30 seconds, I mean, that's a nice round number. What might that 30-second number be? Timeout. We're making the exact same request. What's happening here is the proxy server is willing to talk to us a little bit. It's willing to challenge us for authentication, but when we finally send our request across, we never get a response back. We never hear back from it. It just kind of goes off into Never Never Land. And after 30 seconds, the client gives up and it says, well, I don't know what happened, but I'm going to try again. And it goes ahead and it tries the same thing again. And we go ahead.
30 seconds is a long time.
I'm sorry?
30 seconds can be a long time.
Yeah, in the world of networking, if you're sitting there waiting for something to happen, I mean, 30 seconds is days. I mean,
I think I can tell what's going on. Because what happens is the user goes to a web browser, it asks if the proxy has an auto detection system set up. So it asks for required authentication, and Windows client will send the current logged in user to the system. And it probably fails. Or
It-
it can be looked at.
It doesn't fail because we get the responses back. The challenge response process, if we look into this a little bit,
Oh, but it comes back with, but after it responds, it dies for 30 seconds, doesn't it?
well, after we get through the proxy authentication, we go and we send our request through and the request just sits there. We never hear back, so we don't really know what happened to the request. All we know is it looks like we authenticated properly. Proxy didn't come back with a 401 access denied, or
Yeah.
they didn't tell us, no, you failed, go away.
So they can all that look up for somebody's dead on the back end or something.
Something happened. I mean, we did authenticate, but our request never comes back to us. So we said to the user, well, let's go take a look at your proxy server. Let's go look at the logs. Let's see what's going on. This wasn't a squid proxy, but it turned out that this proxy did not want to allow SOAP requests through. And so rather than telling the user, oh, you're doing something you're not supposed to, it just said, you're not supposed to do that, and it eats it. It just drops the request. It doesn't drop the packets, it just drops the whole request. So in this particular case, it was just on that proxy server. Once the user looked at the logs and shared with us what was in there, we said, yeah, we kind of need that. We kind of depend on SOAP. You have to allow that for this communication. And they went and they tweaked a couple of things on their side, and it went ahead and it took care of the problem for them. So we now have another file upload issue. These silly users and their files. The problem is uploading the file to ProjectWise. The transfer keeps hanging. The logs didn't show anything useful, so we went ahead and we grabbed a capture from a client and from a server. And I very foolishly closed out my Windows Explorer session. So we have a whole lot of packets on the client here. We're already filtered down to port 5800 because didn't want these packets to be too big. So where can we start?
Bottom.
That's not a bad place to start. Ooh,
Looks black.
that doesn't look good. Red and black. That's never a positive sign. So what do we have going on here? Now we've got duplicate acknowledgements, we've got retransmit, so we have packet loss. If I scroll up here just a little bit, see if I can find a Cincinnati stream. User's trying to download a file, so the user making the request is going to be this 51.60 user. So as we come down here, we can see that the 51.60 users, that's going to be our client, is trying and trying and trying. We're retransmitting, we're retransmitting, we're retransmitting. We're not getting anywhere. So what do we do? Well, let's go ahead and take a look at the server. What's going over on the server side? So where do we look? We can actually look right down at the bottom again. And we see a lot of the same stuff. We can see we've got retransmits, we've got duplicate acts, so there's something, all kinds of bad going on the network here. Well, there's a couple of things we can key in on here. If we look here, we've got a 30-second delay. And if we look at the port here, this is actually a separate stream. So I'm going to go ahead and follow stream on the one that's not behaving so that we can go ahead and we can look at just what's going on there. And we can see that, who are we getting acknowledgements from? We're getting acknowledgements in from the client. We're trying to send them duplicate acts, they're not getting there. So what we have here is the client seeing the acts coming in from the server, but the server isn't seeing the retransmits coming back in from the user. So we can tell that we've got a one-way failure here. Packets are going one direction, they're not going back the other direction. So what do we do? Well, in this case, we can go to and talk to the user and we can say, look, the traffic's not flowing here, something bad is happening, what do you guys have in between? The user's going to come back and say, oh, we've got routers and switches and we've got this whole network infrastructure in between. How do we narrow down where in between the client and the server our failure is coming in from? Got to move the dissector along. You got to capture at different points. You've got to narrow down. You know, maybe they've got a huge WAN in between these two sites, and we've got to narrow down exactly where the problem's coming from. So in this particular case, the user went ahead and took the issue and never really bothered to tell us what they had done to fix it. But we're going to take this same example, and we're going to look at it again from another user, and this user was a little bit more willing to work with us. And in this particular case, we have 5 captures. So I'm going to go ahead and start off with the client server. What's happening in this particular case is the user is trying to log into the data source, and it is intermittently failing. Sometimes they can log in, sometimes they can't. Kind of hit and miss. Some data sources are better than others, some are worse than others. It's a real bizarre issue here. So from the client-side capture, what can we see here? Well, we've got retransmits, that's pretty obvious, it pops out. But if you look at the very beginning of this capture, there's a real weird signature in here. We have a synac, ack. That's bizarre. That doesn't seem like the normal way for a TCP handshake to happen. The double ACK is kind of understandable. We got 2 SYN, so the client very politely is going to ACK to us. I don't know why you sent me 2 SYN packets, but I'm going to acknowledge both of them because I want to be friendly. If you look at the delta time here, it's about 234 milliseconds for the first SYNAC to come in. But when's the next SYNAC come in? Instantly. That's weird. That doesn't make a heck of a lot of sense whatsoever. And we get down here, we go ahead and we send a little data to the server. I'm sorry, those are the ACKs. We go ahead and we send a little data to the server. You can see we've got a push ACK here. There's not much, but there's a little bit in the packet payload. And we retry, and eventually the user gets upset and closes out of the application, and we just hard shut down the whole connection. I don't know if you're still listening, but if you are, we're going away. We've got other things to do today. So if we go ahead and we look at the server, see a much different story on the server. What do we see here on the server? Well, we don't see a double SYNAC, which is interesting. So what's that tell us right off the bat?
Well, we're seeing a lot of retransmission.
We are seeing the retransmissions. We don't see the double SYNAC because the server did send the double SYNAC. So that's something to note. That kind of says to me, well, something in the middle is doing something a little funky.
Maybe the server never received.
Well, a SYNAC would be coming from the server. If I say hello, you're supposed to say hello back. If you say hello, hello, I don't know why you did that, but we should see it in the server-side capture. The client did hear a hello, hello. So somebody else must have shoved another hello in there. Another SYNAC in there. You're right, we see the retransmits. If you look at the client and the server here, we can see from the SYN that the client's going to be our 96 address. So we can see that we get the data from the client, and we get the data from the client, and we get the data from the client, and we get the data from the client. Well, what does the server do after each one of those packets come in? It acknowledges it. It says, yep, I got it, thank you. Yes, I heard you the first time, thank you, I did get the data. So this is very much the same situation we had in the last case, where the packets are flowing one direction, but the responses just are not coming back. Now the connection started to work a little bit. I mean, we got the SYN-SYNAC ACK back and forth. You can see that we've got the double ACK in here. So the conversation started to work a little bit, and then it all kind of disintegrated and fell apart. So we went back to the user, and we said, well, there's something funny going on here. I'm not sure what's going on, but there's something funny. Tell me a little bit about your network. Well, this user had a rather large network, and they had riverbed devices in there. Great, love riverbed devices. They have dump cap built right into them. They are a beautiful place to capture packet from. You don't have to spam ports. You don't have to walk around with laptops and plug in. You just run around on the riverbed devices. It's really nice. So in this particular case, we had the client go to the VPN riverbed. This was their local office, and they had a VPN back to corporate. Back in corporate, they had a WAN riverbed. This was kind of the hub riverbed that you had the VPNs coming in, and then you had the other requests going out to the sites. The other sites, I believe in this case, were MPLS, not terribly important in connecting technology. But when we got to that other site, we had the site-side riverbed. And this is where the integration server actually lived. So we went ahead and we got captures from all 5 points, and it was all synchronized so we could see what's going on. For some reason I cannot do multi-select with this. So, Happens to be the first one that came up here. This is the site-side riverbed. What do we see? What does this traffic look like here? Remember the site-side, this is the site where the server actually lives. Kind of looks like the server-side capture, doesn't it? If we flip back and forth here between this and the server, they're more or less identical. There we go. Use the right tab here. So they're basically identical. There's minute differences in there. The timestamps are fuzzy just a little bit. I mean, every device is off by a few nanoseconds, but they're basically the same. So what can we rule out? We go back to our little network layout here. We can actually rule this entire site out. Whatever ad is happening isn't happening at this site. So which site do you guys want to look at next? You guys want to look at the WAN, or you want to look at the VPN? You want to look at the client side, or the hub in the middle? The WAN? All right, we'll look at the WAN. Doesn't really matter what order you move across these different things in. It's whatever order you decide to pick. There's no magic formula to it. So this is interesting. What do we see here? What does this look like? Now there's retransmissions. This actually looks a lot like the client side. Now if you note in here, we have a SYN and an ACK. There's no SYNAC. Why isn't there a SYNAC? Riverbeds are busy devices. This is in their main data center. This is handling connection from people coming on all over the place. The riverbed missed those two packets. It happens. It's not the end of the world. It's not, oh, that's the problem. The dump cap on that server just misses the packets. It happens. Don't worry about it. Don't get too hung up on it. But this looks, except for the syntax missing, a tremendous like the client side. So what does that tell us going back to the network diagram? Do we need to look on the client at this point? The WAN sees the same traffic that the client sees. The site sees the same traffic that the server sees. So where's the difference have to be?
What does the site riverbed do?
That's just the riverbed at the site where the server is. You can see we've got three different networks here. We've got the network where the client lives that happens to have a riverbed device. We've got the corporate data center that has a riverbed device. And then we have the server-side site that has
the WAN pull like goes down from the site or something. It looks like it's forwarding, but it's like all communication now, like the WAN or whatever is acting as the server. All communication has to go to the WAN box.
It basically does. The way this user's network set up is all the site traffic goes into the main data center for processing. The main data center sends it out to the next site. So it's kind of a hub topology.
So all the data has to flow through the WAN riverbed?
Correct.
Both directions?
Both directions.
Packets are dropped.
Not in this particular case, because what does the WAN riverbed look like? It
Mirrors both sides.
Well, it mirrors both sides, but it shows the same data as the client. So what this does is this takes this entire network diagram and it isolates it down. The problem is either on or between the site riverbed and the WAN riverbed. So we've taken out the entire site-side infrastructure, and we've taken out the entire client-side infrastructure, and most of the data center infrastructure, and we've narrowed it down to just between these two devices. So we went back to the user and we said, well, it's got to be between these two devices. It might be the two devices, but yeah, it's got to be somewhere in there. So we said to the user, well, how's your network look like? What do you guys actually have between these two different sites? They said, oh, we got routers and firewalls and redundant connections. And redundant connections, that kind of sounds interesting. Tell me a little bit about the redundant connections. Is it active, passive, load balancing? What they told us was it was a failover. It was a, not a failover, it was a load failover. When the load got sufficiently heavy on WAN link 1, the traffic would start to fail over to WAN link 2. They had firewalls, independent firewalls on each side of these WAN links. What we eventually found out with this user is that when the traffic started to fail over, they never told the firewall on WAN link 2 that the traffic might fail over. It never told it the connections were coming through. They never clustered the firewalls on either ends of this. So when the traffic started to fail over, the responses were coming back from the server, and that firewall was just dropping the packets. It wasn't being polite and sending resets or sending anything else that would allow us to key in on what's going on. It just, oh, drop the packet. I don't know why you're sending me this. Dropped it on the floor. So that was that. That's time. I certainly have other captures I can go into, you guys. If you guys really don't want to eat lunch, but